So despite the fact that the Rayleigh-Jeans law was correctly treating thermodynamics and was correctly treating light as an electromagnetic wave, its steadfast refusal to get an answer that agreed with experiment or even made any kind of physical sense whatsoever was becoming increasingly frustrating to another researcher who was working on the problem, who went by the name of Max Planck. And in 1900, Max Planck started getting so frustrated with this problem that he started making some really crazy assumptions. And one of the assumptions that he resorted to finally worked. It had no physical justification whatsoever. He had no reason for it. He was going to go back and try and fix it later. But what it did do was it gave him the right form for the blackbody radiation spectrum. Classically, if you have light of frequency f that can have any amount of energy of that frequency that you like, you can have a very, very small wave or a very large wave. And the energy in the wave is just related to the amplitude of the electromagnetic wave. But Planck made an assumption that it actually came in little packets. The only energies that it could have were multiples of this quantity. So the frequency times this constant that Planck had to invent, it's now called Planck's constant and has a value that is very small. So because the constant's so small, this amount of energy here is very, very small for any frequency that we're used to. And that means that energies can take almost any value we like, but instead of being continuous, they happen to be discrete. So the energy at a particular frequency has to come in multiples of this HF. So having made this assumption, Planck managed to get the following law for the spectral radiance. Now the Rayleigh-Jeans law was correct at low frequencies and went wrong at high frequencies. Now the Planck's law agrees at low frequencies, but it also gets this curve and the way it dips down again correct at high frequencies. And so it gets the spectral radiance for a black body correct. Let's make sure we understand what this spectral radiance is. And the best way to understand what something is to look at its units. So spectral radiance is how much power is coming off something. And power is just energy per unit time. But the larger the object, of course, if it's all at the same temperature, each piece of the object is radiating the same amount of energy. And so the more surface area you have, the more energy. And so this power is going to be proportional to the amount of area. So the spectral radiance is the energy per unit time per unit area. So that's the surface area. And remember, it's coming off at different frequencies. So if we have a small range of frequencies like this, then that'll have a certain amount of power coming off it with those frequencies. And then we'll have more power coming off at these frequencies. And you can see at low frequencies, there's not very much power coming out. And so the spectral radiance has got the spectrum in it, and so it's also telling us how much power per unit area per unit frequency is radiated off a black body. So in other words, if we take all these slices, all these spectral radiances of different frequencies, and we add them all up, then we're going to get the total amount of power per unit area. And then if we multiply by the surface area of the object, we'll just get the total power being radiated by it. So Planck's law very accurately predicted the radiation coming off bodies, but it had to make this crazy assumption that an electromagnetic wave of a particular frequency could only come in packets of energy in these discrete quantized amounts. And so that was the real question that was sitting there, is why did this work? It's the kind of thing you might expect if light were a particle. You'd expect it to come in little chunks of energy. But it's not the kind of thing you'd expect if light were a wave. And people were very sure that light was a wave. They had Young's double-slit experiment and the Poisson spot, and they had Maxwell identifying light as being an electromagnetic wave from looking at the equations for electricity and magnetism. And all these things were very convincing. And so they didn't really understand why assuming that the energy was quantized was giving them the right answers. And that mystery stayed for several years until Einstein resolved it when he tried to explain a different effect called the photoelectric effect.